Good evening, guys. As you all know, my name is Tembale Tutayeni, and I hope you are fine again in your respective places. So, this is our lecture, which is lecture number 7, and you know, we talked about in our lectures the fundamentals of soil fertility and plant nutrition in general. We also talked about soil reaction in detail. What is soil reaction? How to measure soil reaction in the lab or in the field. We also talked about the importance of soil reaction in crop production and how to maintain soil reaction. So in this lecture, we will talk about soil pH and nutrient availability. So in this lecture, we will cover the following concepts: soil pH and nutrient availability, plant essential nutrients, a recall or a reminder. Remember, we talked about plant essential nutrients in general, the assimilated forms of plant essential nutrients, which is also a reminder, nutrient availability chart, which is also a reminder. But in this lecture, we want to talk about these concepts in detail. Okay. Influence of soil pH on individual plant essential nutrients, soil production, soil pH, and crop production, or the importance of soil pH in crop production. Okay. So let us look at soil pH and nutrient availability. This is just a reminder that understanding that soil pH controls the availability of most nutrients is important for proper nutrient management. Okay? And maintaining the proper pH for crop production is a must for efficient use of other crop inputs. Very, very important. If you want to have good yields or optimum yields for the crop that you have grown in your field, you must maintain an optimal or a proper pH. Now let us look at plant essential nutrients. This is just a reminder. We talked about plant essential nutrients, and we said there are 18 plant essential nutrients or 17 plant essential nutrients. If you read the older versions or the older editions, textbooks of soil fertility, they will tell you that there are 17 plant essential nutrients. And if you are reading the newer editions, they will tell you that there are 18 plant essential nutrients. Okay. So if I ask you, for example, how many plant essential nutrients, if you say there are 17 plant essential nutrients, I will mark you correct. If you say there are 18 plant essential nutrients, I will mark you correct. Okay. But if you say there are 19 plant essential nutrients, I won't give you a mark. In other words, I will mark you as incorrect. If you say there are 16, you are reading the very old versions, of which I want you to be current. I want you to read, your recent, soil fertility material. So if you say there are 16, I will mark you incorrect. Okay, obviously. Now, soil fertility. In soil fertility, we are recognizing 18 plant essential elements, and these elements are broadly divided into two categories. We have non-mineral nutrients and mineral nutrients. Non-mineral nutrients are the plant essential nutrients that are not supplied by the parent material or by the soil itself. Okay. Whereas mineral nutrients are the plant essential nutrients that are supplied by the soil itself. Okay. Now the non-mineral nutrients are three, and these are carbon. These are carbon, oxygen, and hydrogen. Okay. Now the non-mineral nutrients are sometimes called framework nutrients. Why? Because these nutrients are also needed by plants in large quantities. Hence, sometimes these nutrients are called macronutrients also. Okay. So, if we look at the mineral nutrients, are divided into two. We have macro and micro nutrients. Macro means large. Micro means small, less, little. Okay. Now, the mineral nutrients are divided into two, macro and micro. Macronutrients are the mineral nutrients that are needed by the plant itself in large quantities or in high concentration, whereas the macronutrients are plant essential nutrients that are needed in trace quantities or in low concentration by the plant. Okay. Nitrogen is an example of macronutrient, phosphorus, macronutrient, potassium, macronutrient, calcium, macronutrient, magnesium, macronutrient, sulfur, macronutrient. Okay, so there are six macro mineral nutrients. Okay, whereas micronutrients there are nine. We have iron, nickel, zinc, chlorine, manganese, boron, copper, copper, and molybdenum. Now, the macronutrients are further divided into two, primary and secondary. The primaries are your nitrogen, phosphorus, potassium, and your secondaries are your calcium, magnesium, and sulfur. Okay, and we'll talk about this in more detail. So, in which form does the essential plant nutrients are assimilated or are being taken up by the plant roots or leaves? Let us look at this table. On your left hand side, the table shows the elements or our nutrients, our essential nutrients, and at the center there, or the second column, shows us the chemical symbol of each plant essential nutrient, and in the last column or the third column shows us the form taken up by the plants. Okay, now we said it that plant essential nutrients can be taken up by the plant in three forms, in three usable ionic forms. These forms are negative, the negative form, which is an anion, anion. Anion means negatively charged, species, okay? And these plant essential nutrients, some of them can be taken up by plant as neutral or uncharged. That zero denote an uncharged species, okay? Such as carbon dioxide, for example. Carbon dioxide does not have a charge because the oxygen, which is negative, balances the positive charge that is carried by the carbon, ion. But so, and the last, usable ionic form is positively charged, and we call that one cation. So cation for positive, neutral for uncharged, then anion for negative or negatively charged. Now, carbon dioxide is neutral, water is neutral, water and oxygen are both neutral, zinc dioxide is neutral, boric acid is neutral. So carbon, which is a plant essential nutrient, is taken up by plant as carbon dioxide, which is neutral. And oxygen is taken up by plant as water, which is neutral. And hydrogen is taken up by plant as both water and oxygen, which are both neutral. Zinc is taken up by plant as zinc, dioxide, which is neutral. And of course, boron is taken up by plant as boric acid, which is also neutral. Now let us look at the anions. Nitrate is an anion because it carries a negative charge, of course. Both phosphorus orthophosphate. In soil fertility, we call those species orthophosphate. But in chemistry, they call them, hydrogen dihydrogen phosphate for H2PO3 and hydrogen phosphate for HPO4. But here in soil fertility, we call them orthophosphate, okay, species or orthophosphate anion. So both of them are, anion, okay, they are negatively charged. And sulfate is an anion, chloride is an anion, chloride. So, nitrogen is taken up by plant as nitrate. Some plants, they like the nitrate ion, which is an anion. And phosphorus is taken up by plant as orthophosphate anions. Sulfate is taken up by plant as sulfur is taken up by plant as sulfate, which is an anion, and chloride is taken up by plant as chloride anion. Now let us look at the cations or positively charged ions. Ammonium is a cation. Potassium ion is a cation because it carries a positive charge. Calcium is a cation. Magnesium is a cation. Iron and both ion species, that is Fe2 plus. Fe2 plus is ferrous, whereas Fe3 plus is ferric. Both of them they carry a negative, a positive charge, that makes them to be cations, cations for positive. Then nickel ion is a cation because it carries a negative charge, okay? Zinc is a cation, manganese is a cation, copper cation, cobalt cation, and molybdenum a cation. Okay? So some plants they prefer, ammonia or for nitrogen. So nitrogen can be assimilated by plants as ammonium, okay, and potassium can be taken up by plant as potassium cation. Calcium can be taken up by plant will be taken up by plant as calcium cation. Magnesium, iron, and all these things. I think you see now the current what I want to teach you. Now I want us to look at this availability chart at interesting nutrient pH. The black and white one, this one, was produced here in South Africa by Sedara in KwaZulu-Natal using pH. We talked about pH. We said that most soil science labs here in South Africa, they use two methods. The first one is pH water, and the other one is pH potassium chloride. So this one was produced here in South Africa, and this one was produced in America, obviously, by USDA. So now the elements concentration in those availability charts, the ones that are in the yellow rectangle, are our macronutrients, and these ones are our our micronutrients, okay? And we said that most macronutrients are availability increases with an increase in soil pH, whereas the availability of most macronutrients, with the exception of molybdenum, as you can see, with the exception of molybdenum, most availability of micronutrient increases with a decrease in soil pH, but molybdenum, just like the most macronutrients, molybdenum availability increases with an increase in soil pH, as you can see in both availability charts. Okay. Now let us look at these plant essential nutrients one by one. Let us start with nitrogen. While soil pH does not directly control nitrogen availability per se, it does affect microbial activity. Microbial activity affects nitrogen availability, and microbial activity is being affected by soil pH. In acid soil, for example, limit microbial activity and slow mineralization of nitrogen, as well as nitrification. High soil pH can result in significant loss of nitrogen by volatilization, especially when urea is a fertilizer used. As is a surface applied. In other words, if a urease fertilizer is applied on the surface, for example, by broadcasting, what will happen? Significant amount of nitrogen will be lost by volatilization. Volatilization means loss by air, because it will change the form. Urea, you must understand that it's a solid fertilizer, and here they are saying that it will volatilize, it will change form, it will change into gaseous state, hence it will volatilize. Now let us look at phosphorus. Phosphorus availability is strongly influenced by soil pH, obviously, and availability of P is maximized when soil pH is between 5.5 and 7. Acid soil conditions, that is, soil conditions or pH, when the soil pH is less than 5.5, cause dissolution of aluminium in iron minerals, which precipitate with soluble phosphorus, effectively tying it up or fixing that phosphorus in soil colloids. This fixation is most serious below pH 5. Basic soil conditions will cause excessive calcium to be present in soil solution, which can precipitate with P decreasing phosphorus availability. Let us look at phosphorus. The availability of potassium, I'm very sorry. The availability of potassium is not influenced by soil reaction to any great extent. However, in acid soils, potassium is lost through leaching, okay? And the availability of potassium is due to the conversion of exchangeable to non-exchangeable potassium in alkaline soils, particularly if the alkalinity is due to calcium carbonate. The solubility of soil potassium is depressed. Now this lecture is this is very easy. There are no chemical reactions and so on and so forth. So some of these things you can read by yourself. But if you do not understand anything, please don't hesitate. Just ask me. You can ask in our WhatsApp group, or you can ask me directly or via WhatsApp. Now, hence maintaining soil pH between 6 and 7 will generally result in the most efficient use of potassium. Now let us look at magnesium, which is a secondary macronutrient. Magnesium availability is affected by soil pH. For example, in highly weathered soils, low pH can be deficient in magnesium. Magnesium is leached out of the soil due to excess hydrogen, aluminum, and iron, which compete for cation exchange sites. Calcium is another secondary macronutrient. Acid soils are poor in available calcium, obviously, because calcium is what? Is a macronutrient. The availability of macronutrient in low pH decreases, as you can see. So that is why, as in acid soils, calcium availability is poor. Okay. In alkaline soils, the availability of calcium nutrient is always high. However, when the pH is above 8.5, when the pH of your soil solution is too alkaline, is too basic, right? The availability of calcium again decreases. Okay. Sulfur, the availability of sulfur is affected by soil reaction or soil pH, sulfur compounds are soluble in low pH range. However, it is more soluble in acid soils and lost in leaching. Okay, acid conditions which retard the decomposition of organic matter, therefore retard the release of available sulfur. Just like nitrogen, sulfur, sulfur availability depends, a portion of sulfur, availability depends on soil microorganisms. The availability of sulfur present in organic matter depends upon the decomposition of organic matter, which uh, you know which 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 depends on soil microorganisms. If there are no microorganisms, no decomposition of organic matter. If there are a lot of microorganisms, beneficial microorganisms, that is, you know, high decomposition of organic matter. Now let us look at micronutrients. Okay. Now, most micronutrients are directly affected by soil pH, obviously. As the pH decreases, the availability of iron, manganese, zinc, boron, and copper all increase. The availability of these nutrients progressively decrease as the soil pH increases. Their availability also decreases under highly acidic conditions when the pH is less than 5.5. Molybdenum availability, on the other hand, decreases as soil pH decreases. This fact is especially important for legume production. For example, the nodules of leguminous crops contain the enzyme nitrogenase, which is rich in molybdenum. Okay. If soil pH is low and available molybdenum is also low, legumes will appear nitrogen stressed and production will suffer. That is why it is important to go, take your soil samples and go to an accredited, soils lab and test your soils. Don't assume that it will be nitrogen deficiency. Okay. Now, zinc availability in alkaline soils form insoluble zinc salts and thereby reduced. Zinc and copper are also adsorbed on the clay colloids and not easily displaced and hence not available for plant growth. The availability of molybdenum is reduced under acid soils, obviously, because molybdenum is the opposite, right? Molybdenum in soil behaves more like the macronutrients. It is more available in neutral and alkaline soils, molybdenum that is. Copper and zinc availability is decreased by a rise in pH. The critical point for these two elements is pH 6 and 7. Above pH 7, their availability declines quickly. Now, why? Let us look at the pH and crop production. Okay. Now, understanding soil pH should help in diagnostic crop production issues on specific, so that is why, in soil science, soil reaction or soil pH is very, very important. For example, if alfalfa is being grown in a soil with a pH less than 6.5 and the stand is poor, that is the medium, the medium for plant growth, whether it's soil or it's compost or it's any amendment, right? And that is poor. It does not have nutrients, and the leaves are yellow. The first thought should be molybdenum might be deficient. The first method for remedy the situation would be lime the soil and increase soil pH. Surface application of lime to increase soil pH would be slow and would not impact molybdenum ability for quite a while. That is why it is important to do soil test prior planting. Okay. Similarly, If the soil pH is high and the new leaves are exhibiting interveinal chlorosis, that is, for example, the leaves of your particular crop, whether it's maize or whether it's soy, you know, the leaves, when you look at the leaves, there are patches, the veins are yellowish in color, right? That is chlorosis. Chlorosis means yellow. Very easy. Chlorosis, yellow or yellowish. Manganese and iron deficiencies will be the first consideration, okay? Due to the influence of soil pH on nutrient availability, maintaining proper soil pH is important or is vital to a good fertility program. This is soil fertility and plant nutrition, a very, very important course in agriculture. So, and you can't answer, you can't ask questions now, but what you can do after, watching this lecture, if you have something to ask, if you have, for example, any question, burning question, what you can do, you can ask me in our WhatsApp group, or if you are not comfortable to ask in our WhatsApp group, you can ask me directly in this number, using my WhatsApp number, okay, the one that I'm using right now. So guys, thank you, and I hope you will read as much as possible and try to read soil fertility, try to and understand what is going on, because I want you to understand these things instead of ramming them in all. So thank you very much, guys. We'll meet you in another lecture.